data in a most general sense is nothing but a bunch of smaller similar units or units of the same type, which I call data points. So you have a bunch of atoms, so to say. Each atom, which I call data point, represents some object. So, and this could be anything. So one of these data points could represent a cow, and the data set is then a bunch of data points representing cows. Another example, data point could represent a whole forest. So one data point is one entire forest. Another example, data point could represent a day, a whole day. 1st of March is one data point, 2nd of March 2020 is the other data point, and so on and so forth. So I use the term data point or the concept of a data point in a very abstract sense, which makes it very versatile. So you can model almost any application domain as data points, or you can think of data points in any application domain. And I ask you this also in the first assignment. The important thing is that you have to be specific when you start formulating a machine learning problem. What do you use as data points? So what do you define as data points? Do you define data points representing is a data point a person? Is a data point a random variable? Or is a data point a machine learning problem? So in the end, a data point is just some object which can carry information. So which is something that could surprise us potentially. And an object has several properties. So an object is characterized by all the properties or the attributes it has. Like in mathematics, an object is characterized by the properties, by its properties. And I like to think of two groups of properties. One group is called features. These are all properties that we can measure or compute easily. And another group of properties of a data point is called labels. So these are the quantities of interest or the higher level facts. And determining labels is typically difficult. Actually, the goal of machine learning is to develop software or hardware or systems that are able to come up with good guesses or approximations or predictions of the label of a data point based only on knowing the features of a data point. So maybe we look now at some examples. So if a data point represents a protein, then the features could be everything that can be measured easily. Of course, this depends how expensive measurement devices you have. If you have a big lab with big devices that can measure the structure or the three-dimensional structure of a protein, all these are features. And the label could be, is this protein useful in a COVID-19 vaccine? So these were machine learning problems studied a lot during the last year and maybe still studied at pharmacy companies like Pfizer. Another example, a data point could represent some plant, and the features is everything we see. So an image or a snapshot of the plant are features, and we want to predict, does the plant need more water? Important here is again that what you define as data points is a design choice. What you define as the features or what you use as the features of a data point is a design choice. And what you use as the label is also a design choice. As a machine learning engineer, there is no natural choice of features of a data point or a label. So the label might come up as the quantity of interest based on a customer request. So you want to develop some app. For example, you want to develop an app that makes a high precision prediction of the maximum daytime temperature based on the morning temperature. So in this case, we could say we model some ski day or some day as a data point, and we can use as the features of a data point the morning temperature. And the label or the quantity of interest in my case is the maximum daytime temperature, because this is important for the ski waxing. There's one question now. Are labels such properties that their value can be measured or determined exactly afterwards when certain events has occurred? Yeah, so one main source of labeled data points is by looking into the past. By looking into the past, you can get labeled data points, but we are typically interested in getting the label value of an arbitrary data point. So I just give you a data point and you have to tell me what is the label. For example, I give you the data point that represents this day, and you are currently in the morning of this day. So I just throw you a data point and I want to know the label, which is the maximum daytime temperature. And for this new data point, you do not know it. You can only look in the past for similar data points for which you know the label in hindsight. On the other hand, you could ask maybe an expert. So you could ask a senior Finnish citizen, so really a guru for snow and for ski waxing and for how the weather develops. And so you can ask a human expert. Maybe I have some human experts in my neighborhood in Helsinki. So the senior Finnish ski experts, they know, they have a good sense. So when it looks like this, when I look outside the window, the temperature will rise by 5 degrees or by 10 degrees. But since I'm not such an expert, I want to learn, I want to train a machine learning algorithm to do such a prediction. Okay, so here in this case, a data point is some day. And where can we get data? So I also ask you in this assignment to tell me, where do you think we can get data? And I downloaded it. I downloaded today some data, which I get from the Finnish Meteorological Institute. They have open data on the history of weather observations. So I choose here daily observations. And here already, when I make this choice, daily observations, I kind of choose what I mean by data points. So I mean by data points days. If I would mean by data points some finer or some smaller time intervals, some shorter time intervals, like 1 hour, one specific hour, I could also use 1 hour as a data point. Then I would need these observations, the instantaneous observations, which are measured, I think, every 10 minutes. Okay, so already here at this very first step, when downloading the data, I must choose, or I must think of, what do I mean by data points? So is one data point 1 day? Then I might be fine with only using daily observations. Or do I want to use one data point to represent 1 hour? So I make a very high precision forecast, an hourly forecast. So in this case, I need to download these instantaneous observations. So already here, I have to make design choices. Okay, so then I download such a bunch of data points. And each row here, so each row here is one data point, one previous day. So these are just recent days from January. So we see that we have several characteristics. So all the columns here, these are properties of data points. So this is what I mean by properties of data points. This data point, which represents the 4th of January, is characterized at least by this precipitation amount, the snow depth. I guess this is millimeters. So quite a lot already, and the minimum daytime temperature and the maximum daytime temperature. Okay. So this is how data looks like, or could look like, a spreadsheet. But this is only one example of how a data point could look like. So there's one question. If there are data points with features and different features would measure for different actions or labels, so can labels be seen as plural actions or only one complete approximate of a number? So I'm not sure if I really understand the question, but I just want to say you can choose several labels. So a data point can have several quantities of interest. So the quantity of interest could be the maximum daytime temperature and maybe the maximum wind speed during that day. So there are also this is referred to multi-label problems. So there's one question, how accurate should the labels be? Yeah, so this question, accuracy, this already assumes that you have some model. So when I look at the data like this, I can define what the label is. So if I say that the maximum temperature is the label, so then this is the true label, period. But you might have, actually, you might have a model. So you might have some, but we will talk about models later. So it's a bit hard now to talk already about accuracy of labels, because at this moment, a label is just what is written here. So these are the label values, period. We cannot say, it doesn't make much sense to ask if these are accurate labels, because in order to ask such a question, we would need some model or some kind of modeling assumption that involves a measurement, so that takes into account that this temperature, this maximum temperature, this might not be the exact temperature, but subject to some measurement errors or so. Okay, one other question: could we say the label is one of the features? Yes. So yeah, well, at this point, so this annotation here is from me. What you download is just this this spreadsheet, and nobody tells you from FMI you should use this here as features. This is by me, so I choose it. I choose it because I think it might be a good idea. So you can choose whatever column here as label, and whatever column you could choose as feature. So this is design choices. Okay. Another question: what should we do if there is a null value in some data points or features? So this refers to the problem of missing values. And actually what you could do, so let's say here we would not have a measurement. So here there was a measurement error and we would not have a maximum temperature. So what we could do is actually we could use all the data points for which we have all features and learn a predictor for the maximum daytime temperature, and apply this predictor to predict, to come up with a guess of this missing value. So you could learn a predictor and then use the predictor to fill up all the missing fields. This is referred to, this is called data imputation. We will talk about data imputation later in the course. So let's not worry about this problem for the time being. So I just need to check my control here. Okay, so we just downloaded the data from the Finnish Meteorological Institute, and we choose the maximum temperature as the label, and all the other columns could be features. So this is just a design choice. And then we touch already some theory of machine learning. So in machine learning, we want to understand when is machine learning possible and which methods are good machine learning methods. So the first question: when is machine learning possible? And to this end, it's useful to characterize a data set by two numbers. The first number is the number m of data points. This is also called the sample size. And the second number is the number n, lowercase n, which is the number of features. This is the second key parameter of a data set. And these two numbers already tell you, can guide you in designing and implementing machine learning methods. Roughly speaking, machine learning is easy, or you're at the sweet spot for machine learning, or it's an easy game when you have way more data points than features. And here's my rule of thumb. Here's Alex's rule of thumb. Always try to get so much data that the sample size m is roughly 10 times larger, or 10 times the number of features. Okay, so you should have 10 times more rows here than you have a number of columns that you use as features. One good question: is Alex's rule made up, or does it have specific reasoning? Yes, you can make this reasoning precise actually in chapter 6 of the course book, which I just post on the chat. You find the derivation. So if you're not afraid of some linear algebra and probability theory, you can derive that whenever you have less data points, that you have number of features, you have for important machine learning problems, you have no chance to learn a good predictor. So whenever you have less, if the sample size is less than the number of features, when you use standard machine learning methods without any specific tuning, you will fail, and you will fail gloriously. Because when you have too little data points or too many features, you might run into the risk of overfitting. But we will talk about overfitting in round 4 in more detail. I just here want to point out that it's always good to be clear about these two parameters of a data set. So the number of data points, the sample size, and the number n of features. These two are very important numbers that characterize a data set. So they can tell you already a lot about what methods you should use, or what could be the risks in the machine learning when applying machine learning. There's one question: is the label also a feature? So you decide what property of a data point is a label and what property is a feature. You have to choose. Yeah, very good point. There seems to be a typo in the book where the ratio is wrong. So there should be, in order to have an easy game in machine learning, we should have much more data points. M should be much larger than N. Thanks for pointing that out. Unfortunately, you are anonymous. Please send me an email with this hint that I know your name and can grant a bonus point. Okay. So now we have data, we have data points, we have chosen the maximum daytime temperature as the label. And since I now scared you a bit with the ratio of number of features to the number of data points, yeah, maybe just to illustrate this condition here, what would be the number of features that you would use for an image? So let's say you consider data points being snapshots that you take with your Nokia smartphone. How many features can you use or could you think of to characterize an image? A simple snapshot that you take from your dog or your cat or your skis. How many features could you use to characterize an image? How many pixels does such a camera have, or how many megapixels? Any guesses on the chat? Yeah, width times the height of an image. So you would not buy a Nokia phone or a Samsung phone or whatever phone. I cannot make here any advertisement with 1 kilopixel. You want megapixel. You want 60 megapixel. So 60 megapixel would mean you could stack the pixel red, green, blue values into a vector of length 60 million. So n would be 60 million. And then say you want to predict, or the quantity of interest is, does the image show a cat or not? So how many training data points would you need according to Alex's rule? Yeah, you just need to get 600 million images for which you manually tell this is a cat, there's a cat, there is no cat, or there's a dog, there's no dog. So that will not work. So this rule can hit you badly in reality. And the problem is when you use too many features without taking into account the large number of features by using some tricks in machine learning. And we will learn about these tricks later, like regularization techniques. But if you use standard off-the-shelf machine learning methods and you use many features, this Alex's rule is tough. So in order to relax this rule or the constraint, we could make this n very small. So the number of features very small. And what is the extreme case? We use only one feature. We use only one single feature. So according to my experience, a good feature of a data, when the data point is some day, a good feature is the minimum temperature for predicting the maximum temperature. So I just, again, make a design choice. I use as the feature of a data point the minimum temperature, and as the label the maximum temperature. That's it. Yeah, there's one comment. This is why you would apply PCA to reduce the number of features. Yes. So instead of manually picking, so I just here manually cherry picked one feature, the minimum temperature, they are machine learning methods. They are called feature learning methods, and they will be discussed in round 6 of this course. Yeah, if you want to cite Alex's rule, cite instead the machine learning lecture notes provided here. Okay, so then it's always a good idea after you have gathered some data to look at the data. Always get some intuitive feeling for the data. This helps really. And one way to get a feeling is by using a scatter plot. So a scatter plot is a representation of data points by dots or blobs or whatever marker you want to use, which you place in a 2D plane, which is spanned by the feature and by the label value. So the two axes, the horizontal axis are the different values of the features, and these are the different values of the label. In our case, the maximum daytime temperature. And one dot here corresponds to 1 day. And 1 day is characterized by the minimum temperature, the x coordinate, and the maximum daytime temperature, the y coordinate. And from this, you might already get some feeling, is there some relation? So this brings us now to the next component of machine learning, which is a model. Data by itself is useless. So if I just download data and plot it like this, yeah, I can show you the data. You can find it nice. I can send it to colleagues by email, but there's not much gain of data without anything else. To make use of data, we need to interpret it. We need to have a model or some idea how the data is generated or how the structure of the data is. So we need a model.